Hi guys, the video I'm about to show you is actually a string of pictures taken at consistent time intervals. Think strobe light. And you can see the lines there as they pass by for every frame. Again, this is a string of pictures put together. Picture, 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 picture. As each line goes by, the picture is taken.
God, what is that noise?
What is that noise?
Ladies and gentlemen, this is a metronome. So, a metronome is a constant time interval. So let's go ahead and take a look at this image here. So this metronome, think about it as one of those strobe light pictures that we saw in that video. At a constant time interval that takes a picture. So imagine a person who is moving in motion, picture, picture, picture. And we can see that this is a visual representation of motion, of someone moving.
You can see that they're in a different spot every time this stupid thing beeps. Can you make that beeping stop, please?
Think. I won't turn it off. All right, so I want to direct your attention down here at our lovely physics book. And down here we have some other representations of motion. Yeah, so if the camera is taking pictures at the same interval, what would this be? What would this be? What would this be? And what would this be? What's the one thing that's changing in between in all these pictures?
Well, the distance between them.
Yeah, so this one is sort of like the same amount of distance, and these ones it's closer and gets further and gets closer. Now, ain't nobody got time to draw all these stick figures.
Yeah, I get that.
So let's make it simple.
Ooh, dots. I can make dots.
Dots. All right, so what do these represent? Well, let's take a look. Boys and girls, let's roll the ball on the table. We're gonna make what's called a motion diagram. I don't think I mentioned that. Those are called motion diagrams. So the first thing I'm gonna do is I'm just going to roll the ball on the table.
Wow, good stop.
What sort of motion diagram, what sort of dots would we draw? Now think back to those four pictures. What would that motion be represented by? What
Should
sort
they
of
do that
motion
in their
diagram?
notebook right now?
Yeah.
Make a motion diagram of this. Do it again, do it again.
Do it again. Rolling the ball is pretty hard. It's harder than it looks. All right, so now the next thing I'm gonna do.
Whoa!
Make a motion diagram of the motion of the ball on the track. You just did that. Next thing I'm gonna do is I'm going to roll the ball down a track. Now we have already decided that the positive direction is gonna be that way. So as I roll the ball down the track, I want you to think about what the motion diagram for this would look like. That was a lot easier to
Oh, do that again, would you? That was fun. Ah.
do. Okay. What would that motion diagram look back? Now think back to the options that were in your book, and what would that look like? Here's our last one. I'm now rolling the ball up the track. And again, I switched it so that way we're still talking about the positive direction being this way. Maybe I shouldn't include that in there.
That's good.
Okay. All right, here we go. I'm gonna roll the ball up the track.
Yeah, you can do better than that. Do
know,
that
I know.
again. Come on. Ooh.
Let me catch it up there. Okay, I'll do it one more time. What would this look like? Make a motion diagram.
Come on, you can do it. Come on. Come on.
So when we rolled the ball on the table, was it A, B, C, or D?
I think it should be B, Miss Moore.
You would be correct. Why is that? Well, so given our time interval, dink, 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 dink,
Ah, yeah.
we can see that the distance in between each little dot during that consistent time interval is the same distance, which means it's moving at a constant velocity.
Constant velocity. Yeah.
Now, when
that.
I say speed and velocity, they're interchangeable. The only thing is that velocity has that direction component, right? And we moved it in the positive direction. We said, hey, this is the positive direction.
All right.
All right, so now when we rolled the ball down the track, which one is it? A, B, C, or D?
Well, let's see. What happened as it rolled down the track?
So it started gaining a little bit of speed, right?
It did.
Which means that it was covering more ground in the same amount of time. So it's covering more distance. So as you can see, it's getting a little bit faster there,
yeah.
right? So it's definitely going to be C. Now think about when we rolled the ball up the track. When we rolled the ball up the track, when it left my hand, it started off a little bit faster, and then it slows down to a stop when I hold it.
Yeah, it's going uphill.
It's going slower. It's covering less distance in the same amount of time. It's going uphill.
Yeah.
Just like when you get slower when you go uphill. So that would be D.
I like that. Sweet.
Sweet.
And what is that called?
This is called a motion diagram.
That's important. Thank you.
Time for a lab. Uniform or not. First things first. Set up the V channel.
It looks like the letter V.
Sketch the setup. Measure 0.4 meters from the bottom.
First, they got to sketch the setup.
Sketch the setup, people.
Well, you can measure 0.4 meters.
So 0.4 meters is right about here. So right there, okay? From the bottom. And what we're gonna do is we are gonna time the ball rolling from the 0.4 meter mark to the bottom of the track.
Record data. Where are we going to do that, Ms. Moore?
That's a great question. Step into my office. Please pause the video. Make your notebook look like this. All right, let's go ahead and get started. We are gonna do 3 trials so that we can find the average time and then the average velocity.
Okay.
All right, 40 meter mark is right there. I've got it on and go. Time, I got 1.05 seconds.
Okay, boys and girls, on your data table, 1.05 seconds.
Get back here. Yep. Okay, reset. You have to be very athletic to do this. 1.21 seconds. I'm slacking.
So, do you think the difference is the ball or the timer?
Or Miss Moore. Obviously, it's the ball. No, it's the timer.
Why do we do 3 trials, I wonder?
Why? Because we be messing up. And go. And stop. 1.21. Woo! Okay. 1.21 seconds.
What are we supposed to do next?
Next thing we are going to do is find the average time.
How do you find the average of anything?
How do we find it? Well, we're going to add them all up and divide by the number of things that we have.
Oh, okay.
I'm going to go ahead and plug this in. Parentheses. 1.05 plus 1.21 plus 1.21. And then I'm going to divide that by, how many numbers do we have?
3.
Boom. We're going to call it 1.6.
So the average time was 1.16. Now
what are we supposed to be doing next here? So take a look at our screen. We found the average time. Now it's time to find the average velocity.
velocity is a scary word, Mrs. Moore.
Come check it out. Let me help you. So as you recall, our equation for average velocity, this line here just means it's average. Below average. No, average. Average velocity at that much length.
That's the displacement, yes?
Yes, displacement. That's the where we let go of the ball from on the ramp. Okay, so we can do this So we're gonna say equals the displacement, which is this number right here, 0.4 meters. And I'm gonna divide it by my average time. Oh, my average time, which was 1.16 seconds. Now again, the reason that we have an average time down here is just because Miss Moore messes up. I don't know, she's not perfect.
You're
so.
not the only one. Everybody messes up. For example, I got out of bed this morning.
0.4 divided by 1.16. I get 0.34. 0.34. What are our units? Meters divided by seconds. Sweet.
All right.
So that is our average velocity, ladies and gentlemen, for those 3 trials.
Predict how much time it will take to roll twice as far.
Okay, let's do it.
So instead of starting at 40 centimeters, 0.4 meters, we're going to start twice as far, up at 0.8. So what does predict mean?
I want you to make a guess, an educated guess here, based on what we just figured out. We said at 0.4 meters, our average velocity was whatever it was, and now at 0.8, 2 times as far. What do you think the numbers are going to be?
How much time will it take to roll twice as far?
So let's go ahead and do this. Again, pause, make your notebook look like this. 0.8 meters now there.
And write a prediction down.
Yeah, make a little prediction right here.
What's that prediction going to be?
Predict.
While you're doing that, let's take a look around the room. Oh, AP Physics. Ah, that's a lovely arrangement, isn't it?
Let's get down to business. Okay. So now we're going to start at the 0.8 meter mark. So the ball will start here, and I will go 3 trials again to get my average time. And here we go. And stop. Okay, I got 1.71.
Ooh, wait a minute.
Wasn't my first one? It was like 1 point like
Huh.
1.05. Okay, that's not double. All right, reset. Here we go. And go. And stop. 1.78. I think I'm getting better. Okay, last one. And go. And stop. I forgot to button. I pushed the wrong button. And last trial. And go. And 1.66. Average time, here we go. Parentheses. 1.71 plus 1.78 plus 1.66 divided by, how many numbers we got? 3. And I get an average time of 1.72. I'm happier with my numbers this time. And don't forget, these are all seconds. I put seconds there, so you don't really have to, but okay. So how did we do so far? Okay, I thought it was going to be a little bit faster. I don't know. I thought it was going to be twice as fast.
So,
But anyways,
what was the time the first time?
boys and girls, look on your lab sheet.
What was the average time for 0.4 meters?
So it was around 1.15 or something. So we got 1.72. I thought it was, yeah, why is that? I thought it would be like double. Okay, let's do the velocity, average velocity.
Okay.
So my average velocity, I'm going to go ahead and do the distance, which was 0.80 meters, divided by my time, which was 1.72 seconds. Don't forget your units. 0.8 divided by 1.72. And I get my average velocity of 0.47 meters per second, compared to last time it was 0.35 meters per second.
Huh, okay.
Huh. So starting from 2 times as high, my average velocity is, well, it's 0.4 compared to 0.3.
So
I thought it was going to be double. Interesting. So, ladies and gentlemen, make sure you have this written in your notebook. Answer these questions with me. What happened to the velocity as the ball rolled? What does average velocity mean? Where on the track was the ball going exactly the average velocity? Well, let's take a look here. So the first question, what happened to the ball as the ball rolled? Well, as we rolled the ball, did the velocity increase or decrease? Well, you can actually hear it literally going faster. The velocity definitely increased. Now remember when we rolled the ball on the table, the sound was the same, constant velocity, right? Ding, ding, ding. But here, our velocity is increasing as it's rolled. Next question. What does average velocity even mean?
I know.
So when we took the average time, it was, we took into account all three of the trials and we divided it by 3 and we got this average number. It represents the best possible number for all 3 of those.
Somewhere in the middle of all 3 of them.
So, ooh, and I like that word. Somewhere in the middle of all 3 of them. That's important. This idea of being in the middle, this average middle number. So our velocity is sort of our average middle number. So if average velocity is our sort of middle number, average number, where on the track was the ball going exactly the average velocity? Okay, so this has 2 parts to it.
Roll it down the track again.
So if we start at the 0.8 meter mark right here, where at this point, where as I let it go, is it going the average velocity? Well, average is middle, right? So it's going the average velocity right now at the 0.4 mark. But what about when we rolled it from the 0.4 mark? When was it going the average velocity then? Well, don't forget, average means that middle number. So right there at the 0.2 mark. From the 0.4 meter mark, it's going its average velocity halfway through its drop down the ramp. Right there. Okay.
Well, if it was the average velocity in the middle, what was it doing before and after the middle?
So that's a really good question. It was going a little slower, then going faster. Boom, average velocity. And then after that, it's actually going a little bit faster.
It's going faster.
Right? It has to work up to that average velocity. Boom, we hit that average velocity. Then it's going to go even faster over here. So the average is this meeting in the middle, giving us that average velocity. Pause the video, make a motion diagram, dots, of the ball rolling 0.8 meters down the track. Okay, now that you've done that, let's go ahead and do it. So, let's see. Start right there.
The ball went faster and faster as it went down the track, right?
It did. So it's going to cover more and more ground. Okay. So that's my motion diagram. Now pause the video. Make a position versus time graph and sketch the motion of the ball. Sweet. Now let me show you a trick. Okay, so this is, now X is for position. Time is over here.
Oh, I see. You took the motion diagram and made that
Turned it.
on the vertical axis. Oh.
So we've got 1, 2, 3, 4, 5. So I'm just gonna go 1, 2, 3, 4, 5. Okay, so at this time, whatever that time is, the ball was right there at 0. Okay, so right here at this time, right here, it was right there. It was right there. It was right there. You see how I'm doing that? And this last one was right here. Whoops, extra line there. Okay, so here we go.
Oh, I remember that with the
With the clicky thing.
with the clicking thing.
So, oh yeah, that's a good good remember there. So remember when I did the clicky thing and I started close to the wall and then I moved away faster and faster. This time our ball is starting at the top at rest and moving down the ramp faster and faster, and we get that same shape. All right.
Sweet.
Sweet.